Assalamu alaikum. So in the previous classes we discussed about the transient stability and we come to the conclusion finally that in part C, by using the reclosures for a temporary fault, we can increase the stability to a great amount. So in this case I told you that you need to take care about this delta max. It will be now in terms of pi minus delta naught. So here there will be no delta 1 present, that is the angle of this PE3 at which this PE3 will be equal to PM. Here only delta naught is the initial operating angle of the system. So there will be no delta 1. One more thing I will ask you to do, try to calculate its delta CR in terms of delta naught and delta R, and of course in terms of these values, that is the maximum powers and reactances if there are any. So this is the homework. I will see it in the next class. You should have calculated this delta CR in terms of different parameters. You can assume that delta naught and delta R are already given. So let's continue in this. So let's try to do one numerical. So this is almost the similar numerical which we have discussed in case B, that is this one. Yes, this one. Here we assume the fault to be at the middle of the line. Here also we'll assume the same. So the question is like this: find the critical clearing angle delta CR for the system shown below for a three-phase fault occurring at point P. P is at the middle of this line. The generator is delivering 1 per unit power under pre-fault conditions. The generator is delivering 1.0 per unit power, so it means mechanical power and electrical power will be equal to 1.0 per unit. That means PM is equal to PE is equal to 1.0 per unit. So the pre-fault condition, for pre-fault condition, this will be the equivalent circuit. 1.2 angle of delta, this will be xt dash 0.25 per unit, and this is the reactance of transformer, and of course all the reactants are shown on the same base, kV base or this MVA base. So this will be equal to 0.25, this will be 0.15, 0.28, 0.15. So these are the values. So we need to calculate the X equivalent. X equivalent will be equal to this plus the parallel combination of the whole circuit. So it comes out to be 0.25, that is this reactance, plus 0.17, that is this reactance, plus the reactance of this divided by 2. It should have in here 0.15. So it will be 0.15 plus J0.28 plus J0.15 divided by 2. So the two equivalent reactance, that is the reactance between this point and this point, is J0.71. So PE1 will be equal to EV by X equivalent sine of delta. So PE1 is equal to 1.2 divided by 0.71 sine of delta. That comes out to be equal to 1.69 sine of delta. Here P max 1 will be equal to 1.69. Here E is equal to 1.2 and V is equal to 1. So this will require in the equation, you know that. So here first we'll calculate delta naught. So delta naught will be equal to sine inverse PM by P max 1, which is equal to sine inverse 1 divided, because PM here will be equal to 1. It is delivering 1.0 per unit at the start. So 1.69, 1 divided by 1.69, it comes out to be 36.27 degrees, which is equal to 0.633 radians. We require this sometimes in degrees and sometimes in radians. I will let you know where it is used in degrees and where it is used in radians. So during fault, the equivalent circuit will look like this. So this point may be connected to the ground, and the total reactance of this branch will be the summation of these three reactances, that is equal to 0.58. Some value reactance of this will be the summation of these two reactances. Reactance of this branch will be the summation of these two reactances. So it comes out to be 0.29, 0.29. So as earlier, we need to convert this circuit, this delta circuit, into a star, so that after it will be very easier to us to find out the its electrical power. So by converting into star, that means this branch will be equal to this multiplied by this divided by the summation of 3. This branch will be equal to this multiplied by this divided by summation of the 3. And this branch will be equal to this multiplied by this divided by summation of the 3. This branch and this branch will be similar. I have directly write down the values. This will be equal to G 0.145. You can check it on your calculator. This will be equal to G 0.145. And this one will be equal to G 0.0725. So the equivalent circuit of this is this, in which what I have done, I have simply uh, replace these two reactants by a simple reactance, which is actually summation of these two reactances. Similarly, this reactance is the summation of these two reactants, so this is remains the same. So as I have told you, we need to calculate the reactance between this point and this point so that we can calculate the power transfer here. So here we need to have another star delta transformation so that we can calculate this reactance. These two reactants are not important. So while calculating this reactance, that is this reactance, so it will be equal to this multiplied by this multiplied by this, sorry, this multiplied by this plus this multiplied with this plus this multiplied with this divided by its opposite reactance, that is this. So after calculating this, it comes out to be 2.426. So the x equivalent to, you can say it is 2.426, and the PE2 will be equal to 1.2 into 1 divided by 2.426 sine of delta. In this case, this comes out to be 0.495. I told you in the earlier class that this x equivalent to will be greater than that of the x equivalent to 1, which is only 0.71. So when this happens, this comes out to be very smaller as compared to PE1, or we can say Pmax2 is very smaller as compared to PE1, which comes out to be around 1.69. So now the post-fault operation, when the line is removed from the circuit, and this line is removed from the circuit, that means this circuit breaker and this circuit breaker operates, this light has been removed. Now the power transfer will take place only through this line, and this will be our the equivalent circuit. So in this case, x equivalent will be equal to simply the summation of these 5 reactances. It comes out to be 1.0 per unit. So the PE3 will be equal to 1.2 into 1 divided by 1 sine of delta. It comes out to be 1.2 sine of delta, which is equal to PE3 is equal to 1.2 sine of delta. It means Pmax3 will be equal to 1.2 per unit. So we know that this is the relation for this question, or we can say equation for the delta CR, that is Pm into pi minus delta 1 minus delta naught is minus Pmax cos of delta naught minus Pmax3 cos of delta max, Pmax3 minus Pmax2 sine delta 1 is equal to sine inverse Pm divided by Pmax3. Pmax3 is 1.2, so Pm is 1, sine inverse 1 divided by 1.2 is equal to 0.985 radians, so delta 1 is equal to 0.9851 radians. So delta CR is equal to cos inverse Pm is 1, pi minus delta 1. Since I have told you that whenever these angles are used without cos, sine or tan, they have to be in radians always, irrespective of what is the condition. So the angles should be in radian. That is why here, since there is no cos delta 1 or something, sine delta 1 or something else, so we have to use them in radian. So this will be pi minus 0.958 minus 0.633 delta naught minus 0.495 cos of this. Here it can be in degrees or in radians. If it is in degrees, so you have to change the calculator mode in degrees. If you are using the angles in radians, you have to change the mode of the calculator in radians. That is all in difference. Here you can use in both degrees and radians, but here only you cannot use in degrees. Minus 1.2 cos of 0.9851. So this is Pmax3 is 1.2 minus Pmax2 is 0.495. So after calculating this, this comes out to be 0.858 radians, that is 49.15 degrees. This is the critical clearing angle. That means for this system to be stable, the fault should be cleared before this delta reaches 49.15. So if it is cleared after this, the system will be unstable. If it is cleared before this, the system will be well stable. So this is how we can calculate the delta CR. It is just identifying the different values and putting the values into the derived formula which we have already derived in the previous sections. Okay. Now usually, as I have told you, that our system engineer is usually interested in critical clearing time, not in the critical clearing angle. So by solving the swing equation, as I have told you, it's a nonlinear equation. It's very difficult to solve, and we have some methods of solving this. So these methods are known as numerical solution of swing equation, which gives the critical clearing time. So this method is also known as point by point method of solving the swing equation. It is used to find out the critical clearing time. It is used to calculate the critical clearing time. I have just mentioned the name of the method which is used to calculate the critical clearing time, but that is beyond the scope of your syllabus, which will not be discussed. But please try to remember this, that the point by point method or numerical solution of swing equation is a method that is used to calculate the critical clearing time. And this is a numerical solution, which because the swing equation is a non-linear equation and we need a numerical method to solve it. We have discussed earlier there were different methods of improving the stability. So that was the steady state stability. Here also we have some methods which are used to improve the transient stability. The first one is the increase in the system voltage, that is use of area. This is also used in case of uh, steady state stability, because I have told you there are two things which you need to keep in mind, that while improving the steady state stability we have to increase the P delta peak, P delta curve peak, and while increasing the transient stability we have to increase the area of the P delta curve. So when peak is increased, automatically area will also increase. So increase in system voltage will result in increase both transient as well as steady state stability. So use of high speed excitation system, they are used to improve the steady transient stability, not steady state stability, because when excitation systems are very fast, their voltages can be, because during the fault voltage fall down. So when we use the fast excitation system, they can improve the voltage, increase the voltage, so that again the uh, value of the Pmax will increase, and it results in an increase in the area. Reducing that system transfer reactance, again the same reason, it results in the increase in the Pmax and hence the area. Use of high speed reclosing breakers, as we have discussed in the case C, when we have high speed reclosers. So by using the reclosure we can increase the decelerating area. Decelerating area increasing means the improvement in the stability. High speed means the delta R will be very slow, very less. The lesser the delta R, the more will be the decelerating area available for the system, and the more will be the stability. So these are the earlier methods which are used in the system. There may be some other methods which are the recent trends, that is the use of HVDC links, because in case of DC transmission uh, there is no problem of stability, because stability is only related to the AC system. DC system there is no stability, because there will be no phase angle which will be responsible in the power transfer in case of a DC. So there will be no sine delta. So there will be no there will be there will not be any curve which has a portion where the electrical power decreases, as in the case of AC, because in case of AC electrical power decreases for delta is equal to 90 to 180 degree, which is the prime reason for the instability of the system. Like in case of HVDC there is no such case. Braking resistors, these are actually used to in power systems, because in case of three-phase fault you can see that the electrical power will reduce. So whenever the fault occurs, electrical power reduces, whether it's a three-phase fault or any unbalanced fault. These braking resistors are used to increase the electrical power in the unbalanced faults. They are usually connected in neutral of the generator. Whenever the unbalanced fault occurs, the current flows through this. Since they are resistor, they result in the power loss, and the power loss will be in the form of electrical power. Electrical power has increased, so that the total accelerating power, that is Pm minus Pe, will decrease. So when accelerating power decreases, the chance of stability will increase. Short circuit current limiters are used to actually limit the short circuit current. And short circuit current is limited, this acceleration will also be limited. Turbine fast valving or bypass valving, because this is actually towards the input side of the generator. Since we assume in the previous cases that the mechanical power will remain the same, when electrical power decreases, these two are used to decrease the mechanical power. So when mechanical power decreases, this accelerating power, that's Pm minus P, will decrease, and hence the stability will increase. These five are the recent trends. This was about the stability of the system. Let us now discuss some more important things. Let's come to now the transients in the power system. So what is transient phenomena? First, it is an aperiodic function of time and has a short duration. So we can say it is a voltage or a current surge or current wave, for example, voltage or current surge, which are aperiodic, which are not repeating its pattern after some time. They are of short duration and they have high amplitude. I have not written it here. So high amplitude, short duration, uh, aperiodic signals, which are the function of time, are known as transients, or we can say surges. They are very dangerous, and to protect our power system from these transients or from these surges, we need to first study them and accordingly design some protective devices to protect our power system from these surges and transients. First, let us discuss what are the main causes of these voltage and currents, because momentary excessive, because they are very short duration. That's what is meant by the momentary. The first one is the lightning. Lightning is the cause for this transient phenomena. Switching, when we put on the load to the system, or when we put off the load to the system, or in other words, when we open the circuit breaker or close the circuit breaker, that's what's meant by switching. This results also the transient phenomena, or we can say surges on the system. Short circuits will also result in the same, and the resonance. Whenever there is a resonance between the capacitive elements of the power system and the inductive elements of the power system, it results in the resonance, and we know that the resonance results in the excessive voltages in the system. Out of these, lighting and switches are the most common and usually the most severe. So resonance and the short circuits, they are not usually uh, most common. Most common are lighting and switching, because switching we are doing deliberately, or we are doing it on the routine basis. In lighting, we know it will be there on one or other day. So the most common will be among these two also will be the switching. Resonance is a rare case, and short circuit will also take place, but not as much as switching and lightning. And they are usually the most severe cases as well. Now, before going this transient, it is also defined in terms of impulse voltages. As I have told you, that is an aperiodic function, is of short duration, and it has got high amplitude for that short duration. So what is an impulse voltage? It is a unidirectional voltage that rises quickly to a maximum value and then decays slowly to zero. So again, it's of similar type, transient voltage, or you can say surge. The only difference is that this impulse voltage is unidirectional. This can be unidirectional, or this cannot be unidirectional. It can have both direction. We can say uh, it may change to the other part of the zero as well. So the wave shape is referred to be as T1 cross T2. It is actually usually referred to as, or it is this impulse voltage is known as T1 cross T2. What is this T1 and T2? I will let you know. For example, for an international standard wave shape, the T1 and T2 is equal to 1.2 into 50 microseconds. So we can say 1.2 microseconds into 50 microseconds. So this is the standard impulse. What does this mean? T1, T2. This T1 means the time it requires to reach it is 90% of the maximum value, that is here 1.2 microseconds. It has reached here up to this, and this T2 represents when it comes down slowly to the value of 0.5 again, that time is the t2, and in this standard case it is equal to 50 microseconds. So it has reached to 90% of the maximum value in 1.2 microseconds, and then the maximum value of this at this point, and then it slowly gradually, or we can say slowly or gradually, it comes down to its 50% of the maximum value in 50 microseconds. This is a standard impulse, and this impulse actually is used to test the different equipments in our power system, whether it's a transformer, whether it is as an insulator, whether it is some other equipment which is used in our power system, because we're assuming that the impulse voltage or the surge are of this nature, and we usually test them for this voltage. This voltage will be available in our labs, high voltage labs. So I hope you understood the difference between transient voltage. It's again, I will repeat it now. It is an aperiodic voltage, aperiodic voltage or current, which has high amplitude, but it is there for short duration. Lighting and switching are the main causes for them, and they are the severe ones among the four. And the impulse voltage is a unidirectional voltage which rises quickly and then decays slowly to zero. This impulse voltage is usually referred to as T1 and T2 voltage, where T1 is the voltage it reached to its 90% maximum, and T2 is where T1 is the time, which is required for it to reach the maximum 90% of the maximum value, and T2 is the time it slowly decays to the 50% of the maximum value. So classification of the surge based on speed. The first one is the surge phenomena. It is the very extremely fast transient. You can see it is of the order of microseconds. Short duration phenomena. Short circuit phenomena is the medium fast transient, and transient stability is the slow transients. So here we are usually talking about the extremely fast transients. These two which we have already covered in the stability study. Now the traveling wave concept. What does this traveling wave or the propagation of surge means? Please try to understand this. Let us say we have a transmission line, and we have a switch over here. It is connected in series with this transmission line and this voltage source, and we have a load. So when the switch is closed, at the instant of switching, you can see that this we are assuming before this that this circuit is lossless, or the transmission line is lossless. There is no R and G present in this, and all the capacitance and inductance, they are uncharged. Their initial value is 0. So when the switch is closed, you can see that since this is uncharged, the initial value here is 0, the initial value here is 0. So upon closing the switch, this will act as a short circuit, this will act as a closed circuit. The voltage across this will be 0. The current through this L1 will be 0. When this happens, same will be in the other section. We can see there will be no voltage in this. Now, since we know that this capacitor will not allow the instantaneous change of the voltage, and this inductance will not allow the instantaneous change in the current. Now the voltage will build up slowly across this capacitor, and when some value of the voltage will appear across this, the current will start flowing through this inductor, and that will be also gradually. When the current flows through this, there will be the charging of this capacitor, but it will be definitely delayed by this. This will charge, after that the current will flow through this, and then this will charge, and we can say that the charging of this capacitor will delayed by this charging by the charging of this capacitor by some finite time. And this is charged upon certain value of this charge, then this inductor will also allow the current flow, gradual current flow, and then this continues up to all the sections. We can say that so unless the capacitor C1 is charged to some value and the finite current flows through this L1, charging of C2 through L1 is not possible, which is of course takes some finite time, which I have already told you this. The same argument will apply to the third section, fourth section, and so on. So we can say the voltage will build up in the successive section gradually. It will not build up instantaneously, because of the presence of a capacitance in the system, capacitance and inductance in the system. The farther away the sending end, the greater is the delay. As we can easily see this, the farther away the this receiving end from the sending end is there, you can see there will be more sections, there will be more delay in the propagation of this voltage. The gradual build of the voltage over the transmission line conductors can be regarded as though a voltage wave is traveling from one end to another end. We can regard this as a voltage wave which travels from sending end towards the receiving end. Because like a water wave that travels from one end to another wave, this behaves in a similar manner, which travels from this side to this side over a finite time, because it will not flow from this sending end to receiving end instantaneously. It will take definitely some time because of the presence of capacitance as well as inductance. If the applied voltage is a form of surge starting from zero to zero and return again to zero, this is the voltage, that means the impulse type of voltage. So it can be seen that the voltage on the internal capacitor rises to some maximum value and then return to zero again. If we take this capacitor C3 and we take this impulse, if we send this impulse voltage from here, you can see if this will charge first from this point to this point and then again go towards the zero. But the charging of this from 0 to maximum and then to 0 will be delayed from this one, from charging to 0 to maximum and to 0 again, and similarly this will be delayed from this. So we can see that this surge has traveled from this capacitor to this capacitor and then this capacitor to this capacitor over a finite time. The disturbance of the applied surge, that is this impulse voltage which I have just discussed to you, is therefore propagated along the line in the form of wave. So we can say that this impulse which charge this capacitor first and then this we can say that this surge is propagated in the line in the form of wave, a wave that has traveled from sending end to receiving end. Thus, such a propagation of sending end voltages and current condition along the line is called a traveling wave. So such condition is known as the traveling wave. So I hope you understood it, how the wave is traveling. It is actually because of capacitance and inductance which make the voltage or current to travel like a wave. Now speed of the propagation. We'll see how the speed of the propagation, what is the speed of this propagation and how it is related to different things. Suppose that the wave after time t has traveled through a distance of x. The value of the voltage and current waves at the starting remains the same throughout the travel, as we have assumed the lossless line. We have assumed it just before. Consider a distance dx traveled by the wave in time dt. The electrostatic flux is associated with the voltage wave and the electromagnetic flux is associated with the current wave. So electrostatic flux will be change between the conductors, this is charge between the conductors of the line after distance x, that is given by, because electrostatic flux is nothing but charge. So charge is equal to C into V, but here C is capacitance per unit length, and for the length of x, total capacitance will be Cx. So charge will be equal to C V into x. So current I will be the differentiation of Q with respect to T, that is dQ by dt, that is equal to I V into C into dx by dt. Dx by dt is the velocity of the traveling wave, which is denoted by V. So I is equal to V C into small v. Similarly, electromagnetic flux linkage is created around a conductor due to the current flowing into them after distance x is given by, that is the psi flux linkages is equal to IL into x, because you know that current inductance, total inductance given in this case is L into x, and total inductance will be flux linkage per unit current. When you multiply the current to the inductance, we get the flux linkages. So psi is equal to IL into x, and we know that d psi by dt will be equal to the voltage. So voltage will be equal to IL into dx by dt. This is again equal to velocity of propagation of traveling wave. Now putting the value of V from first and second. So V will be equal to I divided by CV. So I divided by CV is equal to I into LV. So I divided by CV is equal to I into LV. This I and I will cancel out. That means I will take this L here and this V and V into V square. So V is equal to under root of L into C. This is an important result. So this is the velocity of propagation. I hope you have remember this derivation we have already done in the power system first also. We know that L is equal to 2 pi into 10 plus 7 ln of d by r Henry per meter. This can also be written as u0 by 2 pi ln of d by r dash Henry per meter. So taking r dash is equal to r because it is very close to each other. So L is equal to mu0 by 2 pi ln of d by r. Similarly, C is equal to 2 pi epsilon divided by ln of d by r. LC will be equal to mu0 by 2 pi ln of d by r into 2 pi epsilon ln of d by r. This and this will cancel out. This 2 pi and 2 pi will cancel out. It comes out to be equal to mu0 epsilon 0. So V will be equal to 1 by square root of mu0 epsilon 0. That is equal to 1 by under root of this. The value of this, it comes out to be 3 into 10 to the power 8. This is the speed of the light. The speed of the propagation of the wave is equal to speed of the light. Dividing second by first, we get V by I is equal to I by V into L by C. That's V square by I square L by C. V by I square L by C. V by I has the dimensions of the impedance. So Z is equal to V by I. That's equal to ZC. That is the surge impedance of the line or characteristic impedance of the line. Sometimes natural impedance of the line also is it is known as. So ZC is equal to 400 for the overhead line and 40 for the cable. This was about the speed of the traveling wave and the impedance of the traveling wave that is offered by the transmission line. Okay, thank you.